Okay, so previously we went over the characteristic equation of a second order linear homogeneous ordinary differential equation. And so let's just remind ourselves of what that looks like. It would look like something like this, in which p and y are constants. And so this is a differential equation we're working with right now. And we determined that if you guess a solution that y has some form e to the rt, and you substitute that y into this differential equation, you'll end up with something like this. Okay, and so then we discussed how this polynomial right here was the characteristic polynomial or characteristic equation of the second order linear homogeneous ordinary differential equation. Okay, so now we're going to discuss case 1 of this polynomial. So when you factor this with the quadratic formula, right, you'll get something like this. Right. And so you know that this can have three cases. So the first case is that there are two real roots. The second case is that there are no real roots. And the third case is that there is one real root. So we're going to be dealing with the first item on this list today. Okay, so what happens when there's one real root? Well, you can factor it, right? And so you get your equation and you substitute in e to the rt and you factor out and then you're solving for r, right? So you're gonna, for example, if this was like 2 and 3, you would get something like r squared plus wait, what did I say? Okay, this was 3, this was 2, you get something like r squared plus 3r plus 2 equals 0, and then be like, oh, I can factor that. The solutions to that would be -1, -2. And so then you would get two solutions for r, and then you would get, r1 and r2. And so basically, you solve for r, and you get r1 and r2. So when you get r1 and r2, you can simply just substitute that back into our original form. So you would get e to the r1t and e to the r2t as possible solutions. And it turns out that these two are actually two fundamental solutions. Now what that means is that c1 e to the r1t plus c2 e to the r2t is the general solution for this case 1. It's that simple. So you just solve for r given your two constants, and then you substitute that into the e to the rt form, and you have 2, right? And then you have two constants, and that's the general form. And you might be asking, well, why don't we take the Wronskian of this and see if it actually is the general form? Now, I'm not going to do that, but I am going to tell you that it works, and the Wronskian is never 0, so that does work as the general form for this differential equation of this kind, in which this is factorable into two real roots. So let's do an example, because I don't think I was extremely clear with that explanation. Let's do this in black. Example. So I'm going to give the one that I gave before. I kind of like stated verbally, but I'll write that down. So let's say you have a differential equation, right? And it's y double prime plus 3y prime plus 2 equals 0. And so then you know that your characteristic equation is going to be r squared plus 3r plus 2. And so you're going to solve for r and then equals 0 because, as we stated here before, e to the rt can't equal 0, so this part has to equal 0. And solve for r, and you can factor this to r plus 1 equals 0, so r equals -2 or -1. And so then you would have e to the -2t c1 plus c2 e to the -t, and that would be your general solution. So y equals. And so this would be your general solution. And then if you have two initial conditions to go along with this, then you can solve for the particular solution to the particular case for this differential equation.